We've been looking at this whole idea of diagonalization in the last several videos and how we can use this in various applications and various situations. So we've looked at the case where we have a real symmetric matrix with distinct eigenvalues. Then in the last video we looked at the general diagonalization procedure for the cases when we have linearly independent eigenvectors. And so now we want to look at this one remaining case. So the case where we have a non-symmetric matrix with repeated eigenvalues. In that case, we get what's called a Jordan canonical form. Again, this word canonical is just another term for standard. So it's a standard form that arises in these diagonalization procedures, but under these special circumstances. So we have an n by n matrix A, as before, but we're going to get fewer than n regular eigenvectors. So eigenvectors through the regular procedure that we've discussed in the rest of this chapter. These are called defective matrices because they have fewer than capital N regular eigenvectors, and so we have to get additional generalized eigenvectors. We've hinted at this before, but I haven't actually done an example or talked about how to do it because it actually wasn't clear until now why we would need to. So if we get fewer than capital N regular eigenvectors, so what? That's just the natural property of certain matrices. But here we can see why. If we want to do a diagonalization type process, we need to be able to fill up our modal matrix with capital N eigenvectors that are linearly independent to accomplish that. So in a situation where we have a defective matrix and we don't get the full complement of capital N regular eigenvectors, we need a mechanism, a method for getting additional eigenvectors. They're called generalized eigenvectors. We'll talk about how to do that in a moment. But let's talk about the Jordan canonical form and how is it different from the fully diagonalized matrices that happen in the other three cases when we have linearly independent eigenvectors. So we're still talking about U inverse times A times U, just like before, but now instead of fully diagonalizing the matrix, it's only going to, you could say, pseudo-diagonalize. And what we mean by that is the following. So let's take a 5 by 5 case just to illustrate how this might look. So U inverse times A times U, normally it would produce D, but now it produces J for Jordan canonical form. The eigenvalues are still on the main diagonal, but let's say that one of our eigenvalues is repeated 3 times, so it has multiplicity 3, and the other one, lambda 2, is repeated 2 times, so it has multiplicity 2. So they're still sitting on the diagonal, as before. The elements immediately above the repeated eigenvalues here, here, and here, we could have either 0 or 1. So if we have 1s in some of those, then of course it's not fully diagonalized as was the case before, but it's this Jordan canonical form. Now here's the problem, and this is painful. So the only way to determine whether, in this case, A1, A2, and A3, whether they are either 0 or 1, is to actually evaluate the inverse of U and then do the matrix multiplication U inverse times A times U, just to determine these 3 constants. Now the consolation prize there is in doing that, all that extra effort, you'll hopefully confirm that indeed your eigenvalues are on the diagonal and you have zeros everywhere else. So at least you'll have some confidence that you're on the right track. But nevertheless, it's quite a bit extra work just to determine whether these 3, in this particular instance, these 3 elements would be a 0 or a 1. Now let's talk about the generalized eigenvectors. So let's say we have a situation where we have an eigenvalue that's repeated. It has multiplicity capital K. So there are capital K eigenvalues that are the same. So we need a procedure to get what are called generalized eigenvectors that complement the regular 1 or 1s that we get through the normal process. So remember how we got the regular eigenvectors from the quantity A minus lambda I times U is equal to 0. So we solve for U for a given eigenvalue, lambda n, and that produces our regular eigenvector. Now if we have an eigenvalue, say lambda 1 with multiplicity capital K, then we need to find capital K minus 1, because we got 1 regular eigenvector from that eigenvalue. We need to find capital K minus 1 generalized eigenvectors for the same eigenvalue. Those come from the following eigenproblem. And you'll notice the difference is now it's to the power k. So a minus lambda I to the power k, where k is the number of our repeated eigenvalues. So 2, 3, up to capital K. And so then the k is equal to 1. K corresponds to the one regular eigenvector u1. And so we need to get u2, u3, up to u capital K as the generalized eigenvectors. So let's think about how we could do that. I don't really want to have to take powers of a minus lambda I if I don't have to. So if we can come up with an easier way to evaluate the corresponding eigenvectors, that would be very helpful. So let's go back to the original eigenproblem that produced u1. So a minus lambda 1 I all times u1 is equal to 0. If we wanted to then get the second eigenvector, so the first generalized eigenvector corresponding to lambda 1, then we would have a minus lambda 1 squared times u2 is equal to 0, and we would have to solve that. What I'd like to do, though, is show that the u2 that I get from this eigenproblem is actually the same as the u2 that I get from this expression right here, and I'll show you that that is the case. So this is a minus lambda 1I, not squared, times u2 is equal to u1, u1 being the regular eigenvector that we already have. So this would be a system of equations that is now non-homogeneous. It has a known right-hand side, which is the first regular eigenvector that we already have. Okay, so let me show you that these two are actually the same. So if I take this expression right here, and if I multiply both sides with a minus lambda 1I, so on the left, I'll have a minus lambda 1I squared, of course, times u2. And then on the left, I have a minus lambda 1I times u1. But a minus lambda I u1, that's just equal to 0 from the original eigenproblem that I used to get the regular eigenvector u1. So this is then equal to 0, and so these two expressions are mathematically equivalent. So I can either solve this problem with the coefficient matrix squared, or solve this problem with the same coefficient matrix that I had before, now using u1 as the right-hand side vector in my system of equations. So in summary then, you can generalize this for any k. So we have the a minus lambda 1I, the same coefficient matrix, the same lambda 1 that's repeated capital K times, and then we're looking for the kth eigenvector, and to get that we need the k minus first eigenvector on the right-hand side. So again, for u2, the k minus first is the regular eigenvector u1 that we already have, and then we get u2, and then that becomes the right-hand side vector to get u3, and so forth until we have capital K regular and generalized eigenvectors. So you can see this is quite a bit of extra work. First, we had to actually evaluate the u inverse times a times u in order to get the Jordan canonical form. Now we have to do this additional procedure to get the generalized eigenvectors. So there's not much I can say to ease your pain and suffering here, but one thing at least is that the coefficient matrix in each of these problems, a minus lambda 1I, those are all the same. So if I'm going to solve this, for example, using Gaussian elimination, the Gauss elimination steps, row reduction steps that we use will be precisely the same to get u2, to get u3, again, as many as we need to get our capital K eigenvector. So at least there's that. Now just a couple remarks about this. So you'll notice, again, we still have a minus lambda I, which is a singular matrix. So it's still going to have to be solved using Gauss elimination. It's still going to be the case that we will lose at least one equation from our system of equations when we solve for these generalized eigenvectors. So all of that still holds. And the resulting both regular and generalized eigenvectors are going to be mutually linearly independent. So the set of eigenvectors that we get in the end that we use to form our modal matrix will be indeed linearly independent. So let's do an example. Now, the way I've posed the problem, I've told you to get regular and generalized eigenvectors. I've told you that we're going to need to get a Jordan canonical form. So normally we wouldn't know that. Normally we would just be given an A, in this case 4 by 4. The first thing you look at, the first road sign, is you ask yourself, is it symmetric or is it not? And clearly it is not symmetric. Okay, so fine, file that away. I have a non-symmetric matrix. Then I get the eigenvalues. to see whether they're distinct or not. I get the eigenvalues, which you can use MATLAB or Mathematica for if you'd like. So the eigenvalues are 2, 2, 2, and 5. So I have one eigenvalue that's repeated 3 times as multiplicity 3, and then one that's not repeated. So I have a non-symmetric matrix with repeated eigenvalues. So this is that fourth case where I expect to get a Jordan canonical form. I do not expect to get a full complement of capital N regular eigenvectors. So if we look at lambda 1 is equal to 2, which is repeated 3 times, I hope to get 3 eigenvectors, but in fact I only get 1. I get u1 as 1, 0, 0, 0. As always, there's a constant multiple times that. So indeed, I only get 1 regular eigenvector for this eigenvalue with multiplicity 3. So I need 2 additional eigenvectors. They'll have to be generalized eigenvectors. First, let's look at lambda 4 is equal to 5 and get the corresponding eigenvector for that. And you'll find that that one is 0, 0, 0, 1. So we get 2 regular eigenvectors for our 4x4 system. So we need 2 additional generalized eigenvectors corresponding to lambda 1 is equal to 1. So let's look at that. So I need 2 more. So I'm going to use the expression that we just had in the previous slides, where I'm solving for u2, and I have u1 on the right-hand side. Once I solve for u2, I put that on the right-hand side, which is now known, and I solve for u3. And in that way, I get the u2 and the u3 generalized eigenvectors. Once again, you can see that the coefficient matrix in both cases is the same, so the Gauss elimination steps will be precisely the same. So if you do that, I won't go through the steps. You can do that on your own if you'd like, and you'll end up with this. So for u2, you'll get a general arbitrary constant C1, 1, 1, 2/3. And that's from the Gauss elimination with the u1 that we had before on the right-hand side. Then keep the C1, don't assume any values of C1, keep the C1, put the u2 on the right-hand side, and solve for u3. And you'll find that it is C2, C1 plus 2, C1 plus 1, and 2/3 C1 plus 5/9. Again, from the same Gauss elimination steps, this is what we get. Now we can choose our constants, C1 and C2, arbitrarily, because they're arbitrary constants. And so I'm going to choose zeros. As always, just be careful that when you choose your constants, the resulting eigenvectors are indeed linearly independent. So I end up with my 4 eigenvectors as the columns, u1, u2, u3, and u4. These 2 are regular, and these 2 are generalized. One thing, and I'll emphasize this in my remarks in a moment, you do in this case need to keep them in the order in which you get them. So remember, for diagonalization in general, the order in which you put the eigenvectors in to form the modal matrix doesn't matter. However, here it does. So I got u2 from u1, and then I got u3 from u2. So those need to be in order, 1, 2, 3, and then my 4th one, which is the regular eigenvector. So now, to get the Jordan canonical form, I actually have to invert this 4x4 matrix. Again, use MATLAB or Mathematica for that. Get the inverse of u, multiply times a times u, and then you will get your Jordan canonical form. So you see the 2, 2, 2, 5, the eigenvalues down the diagonal. The 2 is repeated 3 times, and then 5. And then in the elements immediately above the repeated 2's, you have either 0 or 1. In this case, both of them happen to be 1. If I so happen to get 0 and 0 for those 2 elements, then my matrix is diagonalized and we're fine. But in general, we will have a Jordan canonical form that is not a fully diagonalized matrix from this process. So once again, just to remind us, and I hate to keep harping on this, but we just need to remember, in this particular case, so non-symmetric A with repeated eigenvalues, Jordan canonical form, we actually do have to multiply out the u inverse times A times u to get that Jordan canonical form. That's the only way to get it. And as I just said a moment ago, when you put the eigenvectors into the modal matrix, you have to do them in the order in which you got them.